An alternative angular measurement to radians would be our degree measurement. And 1 degree, and here this little circle here is our symbol for degree, and this differentiates between radians and degree. 1 degree is defined as 1 over 360th of a revolution of a circle. So if we were to divide our circle into 360 equal parts, 1 degree would be 1 out of all that 360 parts. So an entire circle then will have 360 degrees. So if an entire circle has 360 degrees, then 1/2 of a revolution would be 1/2 times 360, which will give us 180 degrees here. 1/4 of a revolution would be 1/4 times 360, which gives us 90 degrees. And 3/4 of a revolution would be 3/4 times 360, which gives us 270 degrees. Here we see that from 0 to 90 would be quadrant 1. So in terms of degree, quadrant 1 is from 0 to 90 degrees. In terms of radian, it's from 0 to pi over 2. Here we have quadrant 2, which would be from 90 to 180 degrees, or from pi over 2 to pi in radians. Here we have quadrant 3, which is from 180 to 270, and quadrant 4, which is from 270 to 360 degrees. Now let's look at coterminal angles in relation to degrees. The same definition for radians applies to degrees. A coterminal angle is an angle that has the same initial and terminal side, and it has infinite coterminal angles. To find our coterminal angles, we use theta plus 360 degree times n, where n is once again an integer, since 360 degrees represent one revolution. So here, in this example, we're asked to find a coterminal of 150 degrees. To get a positive coterminal, we can add 360 degrees to this. This is when n is equal to 1. So when n is equal to 1, this is 360 times 1 plus 150, so this becomes 510. When n is equal to 2, we could do 2 times 360, which would be 720, plus 150, which would be 870. And so we can get infinite possibilities. To find a negative coterminal, it would be theta plus 360 times n. This time n could be -1. So if n is -1, it's -1 times 360, which makes it a -360. So it's 150 minus 360, which gives us a -210. So here we can find coterminal angle just like we did for radians, but this time we're adding n times 360 degrees. Similarly, we have complementary and supplementary angles in degrees. In complementary angles, the sum is equal to 90 degrees, and in supplementary angles, the sum is equal to 180 degrees. So here we're trying to find a complement and supplement of 140 degrees if possible. This angle 140 has no complements. Since it's in the second quadrant, it's greater than 90 degrees, so it cannot have a complement. The supplement would be 180 minus 140, since the supplements add up to 180. So if we have 140, our supplement would be 40 degrees. So far, for two angular measurements, we have been looking at radians and degrees. We know that 2 pi radians is equal to 1 revolution, and we also know that 360 degrees is also equal to 1 revolution. If this is true, then 2 pi radians must be equal to 360 degrees. Now if we divide both sides by 2 pi, the 2 pi's cancel here, so we're left with 1 radian, and we divide this side by 2 pi, we get 180 degrees over pi. This gives us a very useful information. We can use this then to convert any radian measurements to degrees. So to convert a radian to degrees, we multiply that radian by 180 over pi, since we know that 1 radian is equal to 180 over pi. If we take our same scenario where 2 pi radians is equal to 360 degrees and divide by 360 instead, the 360 will cancel, leaving us with 1 degree, and this simplifies to give us pi over 180 radians. So 1 degree is the same thing as pi over 180 radians. Here we can use this conversion to go from degrees to radian. So to convert from degrees to radian, we multiply the degree by pi over 180. Here we're looking at a few examples of converting angular measurements from radians to degrees and from degrees to radians. In our first example, we're going to convert from radian to degrees. You recall we said that to convert from radians to degree, we multiply that radian by 180 over pi. So in this example, we're given 3 pi over 2 in radians, and we're going to convert it to degrees, so we're multiplying by 180 over pi. Here the pi's will cancel. The 2 will cancel with a 180, giving us 90, so we're left with 3 times 90, which is 270 degrees. In this example, our radian measurement is -2. Not all radian measurements will have pi. Here's just -2. So it's -2 times 180 degrees over pi. 2 times 180 would be 360, so that's -360 over pi, which gives us -114.59, rounded off to 2 decimal places. In this example, we're converting our degree measurements to radians. So here we're going to multiply by the reverse. So here we're multiplying by pi over 180. So our first example, we have 45 degrees. So it's 45 times pi over 180. We can simplify this to give us pi over 4 as our answer. If you want a decimal answer, we can divide pi over pi by 4, which gives us 0.79 radians. Here we're given 50 degrees and 45 minutes. Another unit for measuring, or a subunit of measuring degrees, would be in minutes and seconds. Just like with time, we know that 60 seconds make 1 minute, and these double strokes here stands for seconds, and this is our minute. And we also know that 60 minutes is equal to 1 degree. So here our angular measurement is 50 degrees and 45 minutes. Since we know that 60 minutes make 1 degree, we can divide our 45 by 60 to get our decimal minutes. So 45 divided by 60 would be 0.75. So our angular measurement in terms of degrees, a decimal degree, would be 50.75 degrees. Now to convert this to radians, we're going to multiply by pi over 180. So 50.75 times pi divided by 180 give us our radian measurements of 0.89 rads. Now let's look at finding the arc length of a circle and the area of a circle, or a section of that circle. To find the arc length S, we use the formula S is equal to R times theta, where theta is in radians. And to find the area of that portion or sector, we use the formula A is equal to 1/2 R squared theta, where once again theta is in radians. Here we have an example. We're going to find the arc length and area of the sector of a circle. Radius is given as 9 feet and theta is 120 degrees. Using our formula to find the arc length S equal to R times theta, R is equal to 9 feet and theta is equal to 120 degrees. Since theta is in degrees, we need to convert it to radians, so we multiply by pi over 180. So 9 times 120 times pi over 180 will give us 18.85 feet to 2 decimal places. To find the area, we use our formula here. So it's 1/2 times 9 squared, our radius, times 120 degrees. Once again, we multiply by pi over 180 to convert our degrees to radians, and this gives us an area of 84.82 square feet.